So last time we talked about how to use a Raman plot and why alpha helices and beta sheets predominate in the secondary structure in polypeptides. Now we're going to look a little bit about the particulars of the alpha helix and the secondary in the beta sheets. So alpha helix is the most prominent secondary structure in a polypeptide. In particular, it's right-handed, and so if you remember from GBio or from organic chemistry. What that means is if you take your right hand, thumb pointing up, you curve your fingers around, it goes in that direction. And just take a look at the alpha helix and see if that is the case. I think it is. Um, I always get bad with spatial relationships, so I can never be a dentist. So alpha helix maximizes the amount of hydrogen bonding. Remember, the hydrogen bond is between the partial positive of one atom in a dipole and the partial negative of another one. And we'll see the hydrogen bonding occurs, something like this within the polypeptide backbone. So here, if we're looking at the direction of the alpha helix, which goes there, the hydrogen bonding is parallel to the axis of the alpha helix, and the R groups project out perpendicular to the alpha helix. And for the alpha helix, there are 3.6 residues per turn. And remember from DNA, a turn is basically 1 point in the from 1 point to another within the alpha helix. So, one full cycle there would be 3.6 residues, which means there's a little bit of a twist to the hydrogen bonding that's there. So here's another look at it, and this is the primary structure here. So this is the polypeptide chain, and what you can see is that the hydrogen bonding is occurring between the oxygen and the carbonyl group and the nitrogen that is one, two, three, I'm sorry, one, two, three, four, or whatever, 3.5 residues away. And you can look at that hydrogen bonding. Can I zoom in here? You can look at that bonding here, right? And you can see that it is a little bit diagonal, right? So it's not kind of straight, immediately perpendicular. This is the direction of the alpha helix there. Here's another look at it. Um, There is a dipole to the alpha helix itself, so we'll see that in a little bit. So there is an amino terminal end of the alpha helix and a carboxy terminal end. And if you notice on the carboxy terminal end, you see a lot of the the carbonyl group, and on the amino terminal end, you're presented with a lot of the amino groups. We'll talk about that in a little bit. And then here's the hydrogen bonding that it follows with the axis of the alpha helix and the R groups projecting out. If you were to look top down the alpha helix, what you see, as I said, is that the R groups here in purple project away from the alpha helix. And this is one of the reasons why we don't have a mix between the L form and the D form of amino acids, is because if you had the D form, these R groups would actually project into the alpha helix and um, disrupt it. And so this is a space filling model of that alpha helix. And there is a very particular structure that allows for the alpha helix to be built in certain different ways, right? And so note here, this is amino acid 1, 2, 3, 4, 5, 6, 7, 8. So that we can build these alpha helices so that they have different faces, right? If this yellow is all hydrophobic residues, you can make an alpha helix that has a face of hydrophobic residues just by putting hydrophobic amino acids in positions 2, 3, 6, 9, and 10. On the flip side, you can build an alpha helix that has a face that has a lot of hydrophilic or charged molecules by putting them in positions 1, 4, 8, and 11. And we see this. One of the measures of a polypeptide, and one of the ways we determine whether a polypeptide is a transmembrane protein or not, is to look to see if there are packing of hydrophobic residues in a particular order. And that tells us where it passes through a plasma membrane, which has a lot of hydrophobic, has a hydrophobic interior, and regions where it does not pass through. And we can actually, just by looking at the sequence, we can determine how many times a polypeptide will pass through a plasma membrane simply by measuring regions of hydrophobic residues versus hydrophilic residues. Note here, if you have two charges, positive charge and negative charge, you want to put them in close proximity to each other. So you'd have a positively charged in 1, negatively charged in 4, and those would stabilize each other via ionic interactions, right? You wouldn't do something like put a positive charge in 1 and a negative charge in 2 because you wouldn't get those stabilization interactions between those two. So from this, we can build out an alpha helix. And my 11th favorite biochemistry question would be to actually say, you know, build an alpha helix that has, a hydrophobic face on one end and a polar face on another end, right? Or something like that. And have you actually make a sequence that goes that. That requires that you actually know all of the amino acids, right? And you know how to use them and how to build an alpha helix. As I said before, there's a dipole here. So note that when you have hydrogen bonding between the positive charge on the amino group and the negative charge on the oxygen group, they kind of cover the charges, but there is at the ends of the helix free either oxygens or amino groups, right? Because they're free, those charges aren't covered, and so on the C terminal end of an alpha helix, you have a net negative charge. And on the amino terminal end of the alpha helix, you have a net positive charge. And so one of the things, if you're building an alpha helix, that you can do is that you can put residues that stabilize the positive charge on the amino terminal end and residues that stabilize the negative charge on the carboxy terminal end. So what residues would those be, right? Well, if you have a net positive on the amino terminal end, you'd want negatively charged residues to compensate on that same end. And so those you might put in what? An aspartic acid or a glutamic acid. On the flip side, on the carboxy terminal end, you have a net negative charge, so you might spike in some positively charged residues to put down there, something like arginine and lysine, right? So those sorts of things, again, knowing your extensive knowledge of amino acid structure and function, you can determine what would go where and what would compensate for what. Okay, so that's what we're going to talk about for alpha helixes. Oh, I'll say one more thing. There are a couple of residues that are called helix breakers. Um, Alpha helix breakers, and those are proline and glycine, all right? And they're breakers for different reasons. A proline, as we saw before in that Rama plot, doesn't have has a very rigid structure due to the nature of the R group, and so therefore it doesn't allow for the um, formation of the alpha helix. Whereas glycine has the opposite problem because it's so flexible, it doesn't give enough structure to allow for the formation of the alpha helix. And so one of the things that you can tell is whether or not you have an alpha helix based on the amount of prolines and glycines that are floating around within a primary structure. So these are ways where just given the sequence of the amino acids, you can begin to get ideas about the type of shapes that potential polypeptide can form. Next up is beta strands or beta pleated sheets. They again are held together by hydrogen bonds. They are depicted in this ribbon structure. Hello, what happened? In this ribbon structure by an arrow. And they have an amino terminal and carboxy terminal loop as well. The way these work is that this is the polypeptide backbone here, and that the R groups project up and down from the polypeptide backbone. There are two types of beta sheets. There are parallel beta sheets in which the direction of the beta sheets go in the same direction. And then there are anti-parallel beta sheets in which they go in opposite directions. You should remember anti-parallel nature from DNA, right? The single strands of DNA come together in an anti-parallel conformation. So in polypeptides, the beta sheets can form in either direction. The difference between the two, besides the fact that the direction of the beta sheets are opposed to each other, is the position of the hydrogen bond. And so here you have a beta sheet um, that's going in this direction, and then here it's going in this direction, right? And note that in an anti-parallel construction, the hydrogen bonds go through in a straight line through the peptide bonds of the amino acids, right? Now, we remember from way in the beginning of class that we saw that the direction of a hydrogen bond corresponds with its strength. And so when you have a hydrogen bond that goes through the atoms, it is going to be a stronger bonding pattern. If you look at the parallel beta sheets, you see, so here, this is the direction, and then you're maintaining that direction over there. And note the hydrogen bonding is occurring at the angle, right? And so these are going to be weaker interactions, right? And because of that, parallel beta pleated sheets or beta sheets are less strong or less stable and seen in fewer numbers of polypeptides, right? And so it's because of the nature of this hydrogen bonding that makes the parallel beta sheet a weaker bond than the anti-parallel beta sheet. And so here's another look at it. This is kind of looking along the beta sheets, and you can see that the side chains are facing up and out from the plane of the beta sheet. And then the hydrogen bonding here, this is kind of a diagonal view of how that looks. And here's one that's kind of looking from the top of the sheet where you can see the direction of the hydrogen bonding in parallel and the direction in the anti-parallel beta sheets. Now, with anti-parallel beta sheets, note if you're looking at the direction, remember all polypeptides has a amino terminal in and a carboxy terminal in, right? So here for an anti-parallel sheet, we don't really have an issue. We can go in this direction in the polypeptide chain, and then you can have any sorts of things, random coil or whatever, and then you just continue along in this direction. And then you have whatever you have, and then you just continue along in this direction. So all of this kind of works with the flow of the primary structure of the amino acids. Now, there are times where you want to have a quick turn, in which you only take a couple of residues in order to turn, oops, that's not the direction that it goes, but in order to turn from one section to another, right? And so you can do this in maybe 3 to 4 residues if you use some qualities of the amino acids, some particular qualities of the amino acids. You can do it in 100 residues if you want it, but you could do it relatively quickly if you utilize what's called a beta turn. And so beta turn is used a lot in anti-parallel beta sheets because it allows for a quick, oops, I'm going the wrong direction. Okay, here we go. For a quick turn to continue the beta sheet. So there are two types, and I'm not going to get too wrapped up into the details, but note here, you're able to make this turn within 4 amino acids in both of them. Um, And in order to do that, you need a special amino acid in carbon number 3 of this turn that allows for some either flexibility or rigidity to make that quick turn, right? Remember, this is an issue. I kind of liken this to a 18-wheeler trying to make a U-turn on a two-lane road, right? It's hard to do because of what? That planar restriction of the peptide bond within the polypeptide chain. So you can't just kind of make that turn easily. So these beta turn structures allow for that to happen. So one of them uses a glycine here. And remember, so this is a glycine in position number 3. That glycine, remember, because it only has a hydrogen in an R group, has much more flexibility. And so you're able to squeeze it a little bit more, right? And so here you're going along. Boom, you put that glycine in there. Because you're able to squeeze it a little bit more, you can make it go in that 180 degrees, and then you stabilize the beta turn with hydrogen bonding between these two carbons. The other one uses a proline. And remember, proline, its R group actually comes back around and links up with the nitrogen, right? And so it puts a conformational constriction on the um, chain, the polypeptide chain. Now, here, this uses a proline in cis. And remember that 99% of amino acids have their R groups in trans with the backbone. Here, when you have a proline in cis, it actually causes a dramatic change in the direction of the polypeptide backbone. And so here, prolines in cis, boom, it forces that chain that allows for it to loop back around, and then again, you are stabilize this beta term by a hydrogen bonding. And so we can kind of see the effects here. So this is the natural configuration of proline and trans. Note that if you look at the general direction of the polypeptide backbone, that it's going all in the same direction, right? Um, you're kind of starting up here, you're ending out down here. However, when you do this in trans, what's going on um, here is that you're coming in, and then because you have this, I'm sorry, in cis, stop that, don't do that. Because you have this in cis, it causes this turn that then kind of goes in that direction. So see here, you've started a curvature that doesn't exist when you're in trans. And that allows for the polypeptide to just kind of reach back around, stabilize it with hydrogen bonding, and do what is effectively a 180-degree turn in 4 residues. All right, so I'll stop that with the beta turn. Oh, there's one more thing that I want to do. This kind of gets into tertiary structure, but you can use a beta turn in an anti-parallel um, beta pleated sheet to do a quick turn, but you can't do this in parallel, right? Because of the direction. So here, the direction of the polypeptide goes here, right? And then within the beta sheet, it continues in the same direction. Well, there has to be some way for the polypeptide chain to come back around, right? So that it can start up here. And so one way that that happens a lot is that we put in an alpha helix that loops the chain back around so it can start up again for a beta sheet. And then an alpha helix that loops the chain back around so it can start up again for the beta sheet. And so we call this a motif, which is linking together a couple of different secondary structures, and this would be a beta, alpha, beta motif, right? So your beta sheet, you have alpha helix that comes around, and then you have a beta sheet again, right? So this is common in parallel beta sheets as a way to maintain the structure of the beta sheet. So now I'll stop, and then we'll talk about and get to tertiary structure and some of these motifs going forward.